Okay, my name is Seth Wenger. I am the Director of Science at the University of Georgia River Basin Center, and it's my pleasure to be hosting this Cyberseminar series called Sustainable Urban Streams, Science to Support Evolving Management Objectives. This is the third talk in that series, and today we're going to hear from Tim Fletcher. Tim is a professor in urban eco-hydrology at the University of Melbourne in Melbourne, Australia. He's the author of over 300 publications on stormwater quality, treatment, and impacts. Along with Chris Walsh, he's the co-leader of the Waterway Ecosystem Research Group, as well as the Melbourne Waterway Research Practice Partnership, a partnership between Melbourne Water and the University of Melbourne, which has the aim of undertaking research to inform and transform policy and practice. Today, Tim is going to talk to us about the Little Stringybark Creek project, which is the world's first full catchment retrofit of stormwater infiltration and management practices, which has been in operation and under active study since 2008 under the leadership of Tim and with Chris Walsh. And just wanted, before I hand it over to Tim, I am going to just make a quick plug for next week's speaker, who is Emma Rosie Marshall from the Carey Institute, and she's going to be talking about contaminants of emerging concern. And then we'll have a break for Thanksgiving, but there'll be one more speaker in early December to finish out this series. With that, I will now turn it over to Tim.
Okay, thanks a lot, Seth, and I hope that pretty much everyone can hear me. It's really a pleasure to be with you and a pleasure to talk about this project. So one of the reasons, I suppose, for being invited to give this talk is that we're at the Symposium on Urbanisation
The
and
host has
Stream
left the
Ecology.
meeting, so at this time, the meeting will come to an end. Thank you, and goodbye.
The automated system just told me the meeting had come to an end, but I'm assuming that's not true. Can someone just tell me they can hear me?
Oh, sorry.
Yeah, right.
Sorry about that. I just, sorry, wrong button. But continue. I'm sorry for the interruption.
All right. And I might get you to just flick over to my slides if you can.
Sure.
Or maybe I can do that. All right, great. And so we presented on this project in the Symposium on Urbanisation and Stream Ecology in Portland a couple of months ago. And oh, now I've got music. Other people music.
Sorry, Tim. Hold on a minute here.
No worries. I can try to give my presentation in a way that's in tune with the music if you want. All right, excellent. Anyway, so I'll get started. So this project is really the product, as you see on on my first slide, of many contributors, and so I want to pay particular acknowledgement to Chris Walsh, my sort of co-leader and co-author of this project. So him and I really came up with the idea of this project in around 2005, and we've been working with a really great group of people to get this project up and running. I've read a few things on how to do a good presentation, and one thing I've read is you need to know your audience, which is a bit hard in a webinar, but for that reason, but not only that reason, I've highlighted Perrine Hamel, who I have reason to believe is in the audience. So if you are Perrine, you might want to type to confirm that you are. So Perrine was part of this project, doing her PhD with us and really contributing a lot to our understanding of hydrology and the transfer of sort of small-scale hydrology to large-scale hydrology in the catchment. All right, so a really important point about this project, so as Seth described, it's really one of the only attempts in the world to apply the type of stormwater control measures or best management practices, as they're often called, at a whole of catchment scale in order to see what happens to a stream. So there are many studies around the world that put in place a particular treatment system, such as a wetland or an infiltration system or whatever it might be, and then study its effect at a particular site. And we really wanted to go well beyond that and to see if you applied these techniques in a distributed way throughout a catchment, would you actually see a response in the stream in terms of hydrology, in terms of water quality, and in terms of the ecosystem. And that seems ambitious enough, but one of the important things to realize, of course, is that you've also got to deal with the human ecosystem, the people that live in that catchment. And so a lot of the lessons that come out of this project go beyond the hydrological or the ecological, and they extend very much into the sociological and the economic. And I'll talk a little bit about those things along the way, and I'll wrap up with a few lessons at the end. Okay, so if we look here at a satellite image of the region around Melbourne, so that embayment is Port Phillip Bay, perhaps not as world famous as Chesapeake Bay, but nonetheless known for its problems of nitrogen accumulation, etc. If we look at that river network, the city of Melbourne is essentially around that embayment. It's spreading all the time, of course, but we can imagine the city as essentially being all around that embayment. And we notice that the network of waterways is less there, of course, as we get into the lowlands, and we've got fairly large rivers. If we think about all of the what we call buried streams, what you call buried streams, I'll show them on the next slide. So here we see those in red, and you'll see that there are quite a few of what used to be little streams that are now buried in pipes. But on the next slide, I will add to that network all of the council drains, so the council pipes. So the ones I'm showing at the moment are just the Melbourne water pipes, so they're the large pipes. And if we add to those the council drains, bang, we see that essentially in that area that is that the Melbourne city occupies, the Melbourne region occupies, basically that whole catchment is just drained by little pipes everywhere. And so it's of course very unsurprising and of course known to us that when you do that, you completely change the water cycle of those catchments. You completely change the pathways of water through those catchments. You completely change the interaction of water and soils, and you completely change, of course, the stream ecosystem. I'll just actually go back there. So the little Stringybark Creek is highlighted in this yellow box, but we'll talk about that a little bit later. All right, so given that we have all of those changes to the water cycle, let's think about just before talking about Little Stringybark Creek as a project, let's just get our minds around this problem of urban creeks. And I'm sure you've all got your mind around it, but I think it's useful to sort of go along this conceptual journey together just to understand where we were coming from and why we've designed the project as we have. So here are two creeks in our region quite close to each other. Sassafras Creek in a really nice, healthy state. Little Stringybark Creek, actually that's a photo that probably makes it look good. Much of it doesn't even look that good. But you can see it's fairly eroded. It's lost a lot of its benthos, and it's not in great ecological condition. We studied, as part of a really big project, the factors that were driving the degradation in catchments around this region, including these two. And we found that, for example, there were more septic tanks in Sassafras Creek, there were more unsealed roads in Sassafras Creek, but oh, that's a pity, you only see a grey box. That's interesting, Aditi, but at least on my screen it's coming out all right. Anyway, I'll keep talking. And so, yeah, more unsealed roads in Sassafras Creek. And so all of the traditional things that we might put down as the cause of degradation actually don't at all suggest what's happening here. What is different between these two catchments is the nature of their urban drainage. So if you look, and I hope that most people can see the pictures, perhaps if someone can just type and tell me if they can see the pictures. On the left you see, oh yeah, so some people do, that's good. On the left you see a very typical road in the Sassafras Creek catchment. It has what we would call informal drainage. The water just runs off that impervious area into the forest and is not conveyed, at least directly, to a waterway. On the right hand side with Little Stringybark Creek, these kind of formally drained roads with a curb and gutter and side entry pits which then divert the water into pipes and then into the stream are commonplace. Pretty much all the roads are like that. If we look at that in terms of the typical indicators that we use of catchment impact, so on the left we've got total imperviousness, and on the right we've got connected imperviousness, or effective imperviousness it's often called. So in other words, the impervious areas that are directly connected into the waterways. You'll see that Sassafras Creek and Little Stringybark Creek have slightly different total imperviousness. They're not hugely different, but all right, there's a little difference between them. But if we think back to those slides with the pictures of the roads, with Sassafras having a lot of informally drained, essentially not connected impervious surfaces, we really see that in this plot, with Little Stringybark Creek having a level of connected imperviousness that's something like 10 times that of Sassafras Creek. If we now proceed to look at a range of ecological and water quality metrics, we'll see that on the top here we've got the same plots as we had before, total imperviousness and connected imperviousness. So again, centering on these, focusing on the two in the center, so Sassafras Creek, the second one, and Little Stringybark Creek, the third one. You'll see that pretty much all of these metrics follow very much the pattern that is shown by effective imperviousness rather than by total imperviousness. So the median dissolved organic carbon jumps up dramatically with effective imperviousness, as does the salinity, the level of soluble phosphorus, same with chlorophyll, and then we've got our two macroinvertebrate composition indices, so IBD2 and Signal, which is commonly used in Australia. And again, we see that something like Sassafras Creek, if we look at Signal, is really in a near pristine condition in terms of macroinvertebrate family composition, whereas Little Stringybark Creek is right down there, sitting in a pretty degraded state near Brushy Creek, which is one of our most degraded waterways. So, not surprisingly, we really formed this hypothesis that the level of connected impervious surface in a catchment is a primary driver of ecological degradation. And we show that fairly clearly with hydrology. This is work published in Walsh et al. In PLOS One last year. And actually it's a great source of amusement in our group that we published 2 papers within about 6 months around the themes of urban hydrology, one by Walsh et al. In PLOS One, one by Burns et al., so our PhD student Matt Burns, in landscape and urban planning. And the Burns et al. Article is cited at a ratio of about 5 times the Walsh et al. One, so Burns misses no opportunity to remind Chris of that. And so in this article, what we showed is that in the catchments with high levels of connected imperviousness, in this case we've got Little Stringybark Creek and Brushy Creek, which is even more so, we see 2 things. One, a big response to rainfall, so nothing that you hadn't learnt in Hydrology 101, but also a loss of base flow. Now we know that this is not, of course, guaranteed to happen, because there are other things that can drive base flow, and we can perhaps talk about that in the questions. But just in terms of what happens in terms of infiltration, etc., we get a loss of base flow, a loss of contributions to base flow when we create these connected impervious areas. So, to summarise, we know that stormwater runoff increases storm flows, reduces contributions to dry weather flows, because we've got these impervious surfaces, which importantly, the runoff from which is efficiently connected into our waterways. And so really the starting point of this project was to try to undo these changes and try to restore more natural flow paths using dispersed in catchment stormwater retention systems. And to do that, we really had to set ourselves some hydrologic and water quality objectives. And I'll go through the hydrologic ones here, because for the purposes of explaining where we're coming from, I think they're the most important. Essentially our aim is to disconnect these connected impervious surfaces, and it's easy to use one word like disconnect, but in fact what we mean, of course, is not just chopping out all the pipes. We still have to deal with issues of flooding, etc. But what we want to do is for everyday rainfall events, the sort of 1 inch and below, to have those retained on site, the water used, etc. And we do that by setting 4 objectives that come directly from that analysis of the hydrograph. First of all, we want to reduce the frequency of untreated runoff, so the frequency of water quality and hydraulic disturbance, if you will, from roughly every time it rains, we get that now, back to some number that's much closer to natural, so less than 10 days a year. So in a natural forested state, of course, when it rains 15 millimeters in our catchments, and this is the case in most places, and of course there are some exceptions, but in most cases, if we get 15 millimeters of rain, you won't get any direct surface runoff into the stream from the broader catchment. You might from just the riparian zone, but not from the broader catchment. And so by using a combination of harvesting type techniques or other retention and infiltration techniques, we can achieve that. At the same time, we want to ensure that the lost base flows we see in these catchments is restored. Now, in some catchments, you may have a different context because you've got significant leaking water supply, but in many situations, you'll have this loss of base flow. And so we want to restore that using a combination of infiltration, but also irrigation, so we maintain soil moisture during summer, etc., which has got other benefits, of course, for the humans. And we also want to restore and maintain the pre-urban water quality concentrations, so we're of course not just having a hydrologic focus or just a flow regime focus, but also a water quality focus. Now, those three are really our primary drivers. So get the high flows back towards natural, get the low flows back towards natural, and ensure the quality is good. Sounds simple enough, but mathematically, of course, if you don't get the volume of runoff somewhere back towards natural, it's actually not possible to achieve these objectives. It's not possible to treat all the water at the level required, and it's not possible to reduce that frequency of untreated runoff. So this is actually a really good opportunity because it means there's a huge resource of water there that we not only can use but need to use in order to restore more natural flow and water quality regimes. And that resource is potentially pretty important. Okay, so if we think then about how we're going to decide how much of that water we do need to keep out of the stream, we rely on some really nice work done by Lu Zhang, published in Water Resources Research in 2001. And what Zhang showed is that using data from all around the world, and I'm pointing to these two curves here, we'll ignore the dots for the moment, showed that for a given rainfall, the band of runoff, the runoff coefficient, would be somewhere in that sort of range between the grassland and forested. So this is in obviously non-urban areas, but in grassland or forested. So it would be somewhere in that range. And we then plotted data from Melbourne streams, and we found that, sure enough, unsurprisingly, that Melbourne streams sort of fit quite nicely in that band. So we could have lots of debates about how precise that band is going to be for any particular case, but such a debate is perhaps put into perspective when we look at how big is the difference between that runoff coefficient we see from forest or grassland to what we see from urban. And so up at the top of the plot here, we've got impervious runoff from 11 sites across Melbourne, and we see runoff coefficients that sort of start at 0.8 and end up somewhere near 0.85, 0.9. And so, in terms of setting our hydrologic objective, the difference between, say, the middle of the forest grassland band of Zhang and our impervious runoff, that represents the amount of water that we have to keep out of the stream. So let's just take the example of an annual rainfall of a metre. So we've got a runoff coefficient that's sort of, let's say, somewhere around 0.25. And so we've got to reduce our runoff coefficient in the urban state of about 0.8 back to about 0.5. So in other words, 65% of the annual rainfall needs to be kept out of the stream. We have to find ways of either using that water or evapotranspiring that water. So a big resource, but importantly, that water that should be in the stream, so that water below the Zhang curve, if you think about it, needs to be infiltrated back into the catchment and contributed to the stream. And so I'll just respond to the question that Tom's posed. So Tom's asked, is infiltration an option? Well, the first thing is that we can't just infiltrate all of that water, because if we do so, essentially we are still going to be increasing the flow dramatically. Now, we're increasing it in a way that's very likely less ecologically damaging than surface runoff, for sure, because we're filtering it very substantially through subsurface flows, and we're mitigating its hydrology very substantially. So sure, infiltration forms a very important part of the strategy, but if we attempted to infiltrate that whole volume, then I think we're going to have trouble. But we need to be infiltrating, let's say, at least the amount that naturally would have been there, and perhaps as Tom is perhaps inferring, a little bit more, and that's certainly a question we're exploring too. But as much as possible, we also want to use that water either through evapotranspiration or through supplying it to households, and I'll talk about that in a minute. Okay, so one of the problems with dealing with these this stormwater issue in a catchment is one of scale. So if we think about a catchment here, so here's a generic catchment, and we've got well, in fact, this is not generic, this is part of the little Stringybark area. If we think about a catchment, and we've got houses everywhere, we've got roads everywhere, so we've got all these little impervious surfaces connected into our streams. And in the past, an approach has been to build some big system right at the bottom of our catchment. And one thing that has always, I think, perplexed Chris and I is that, and I think some of our early discussions with Melbourne Water would say, oh, why are you building this wetland? Well, actually, before I go there, I'll explain that Chris has done actually quite a lot of work showing that the ecological state downstream of these wetlands is often no better or slightly even worse, because even where we might reduce the, for example, nitrogen load in these wetlands, and sure they generally do, that's absolutely, we've definitely demonstrated that, they can also result in creating a regime where the downstream water has very high level of bioavailable nitrogen. So not guaranteed that they're helping our streams much at all, and certainly from a flow regime point of view, they can give some quite perverse effects, because we might mitigate the peak but extend its duration, so our work done on the channel downstream might be increased. But let's leave all that technical stuff aside for a minute. So we ask, say, Melbourne Water, why are you building these wetlands? And they say, oh, we want to protect our waterways. And we say, okay. And we want to, of course, reduce loads of nitrogen going into the bay, which is, again, I would say the wetlands are definitely doing that. But they also state as an aim to protect the waterways. And so, well, hang on, you've built it at the bottom of this catchment, so all of the waterways above it are, unless I don't understand gravity very well, are not affected at all by this this wetland. And if we care about all of these small streams, and the work of people like Peter Groffman and others would suggest actually we really should care about these small streams, because these are very important retainers of pollutants and deliverers of a whole lot of ecosystem services, then we should be thinking about working at scales that are more intermediate. So we might think about these kind of precinct scale systems, and there's a picture of one of our systems from Little Stringybark Creek there. And this kind of approach potentially can work, but generally what you find is that it's not possible to build systems big enough in all cases. So you will find some spots but it won't be possible to build systems big enough in all cases because the stream flows are the flows are so big by the time you get to that sort of sub-catchment level that you're really struggling. And so we really find that what's necessary is actually to work at starting as close to possible at source, doing some larger precinct things as well. But our aim really is to say, well, for each impervious surface, like a house, like a particular road, let's try to deal with it there and then. If we can't, because of some constraints, then we use our precinct systems downstream to pick up what we couldn't get. But if we start there without thinking about dealing with the source, we'll find that we really are struggling because we just will not be able to find the space to build big enough systems to deal with all of those flows. And there are a whole range of other reasons why you might think about at source in terms of, particularly in terms of delivering other benefits to the community. And so again, the photos show the type of things we might be building, rain garden type of systems and rain harvesting systems that supply the households or supply commercial use. So that's a lot of background, but I think it's probably useful to allow me to then explain how we went about, why we went about this project. So our hypothesis was, could dispersed catchment scale stormwater control measures or water sensitive urban design restore the hydrology, water quality and ecological structure and function of a degraded urban stream? So having, we believed, gained a good understanding of what's driving the degradation, could carefully designed systems put in place throughout the catchment result in a change in hydrology and water quality and ecology. To select the catchment, we wanted to pick a catchment that was already degraded, but we didn't want to pick one that was so degraded that we would likely spend $30 million and 30 years getting it back to a state where we might see a response. This plot comes from our study of 16 streams around the eastern suburbs of Melbourne, where we showed that by the time you got to around 10% effective imperviousness, you were completely in a degraded state. And in fact, even at around 2% effective imperviousness, you're already seeing significant impairment. So we had a few options of catchments that were sort of already along that degraded trajectory, but not right out there so degraded that we would be working forever to get them back. Now, I just might make an important point though. I think that doesn't mean that the findings of this work only apply to streams that are kind of not, that are sort of that path and back, because you could argue that we could start working on those more degraded catchments out on the right there, but we're going to take a long time and we're not going to see any response for quite a while before we might start to see a shift. And then there's some of course hysteresis issues to think about. But in terms of policy, we can afford to be thinking in a much longer time frame than we can in this experiment, which we wanted to see a response fairly quickly. So the catchment is fairly typical sort of urban, outer urban catchment. 3 subcatchments, 7% total imperviousness and 5% connected in the northern tributary, 23% and 19% in the central tributary, and 19 and 11 in the southern tributary. So total catchment is about 13%, of which 9% is connected. It's an interesting, if you look at that aerial photograph at the top left there, you see that the lower part of the catchment out to the east is actually more rural, and out more to the west it looks like it's actually more forested, but in fact that's the urban area. And so when you zoom in, you see, for example, on the top right, you've got very typical residential. On the bottom right, you've got a gas station, so sort of fairly typical kind of commercial precinct, pretty highly polluted runoff. And in the bottom left, an industrial area with lots of factories and concrete batching plants and those kind of things. So what we've been doing in this experiment is undertaking a whole range of stormwater works, infiltration measures, rain gardens, rainwater harvesting at small and large scale, using both partnerships with private, so with householders, landholders, and public land, so with the local council. And so what I'll talk about is some of the ways that we engaged with them, and this has really been where I think there's been a fair bit of novelty and some interesting lessons. So before we could hope to really get much progress, we really had to build awareness with the community, and so we ran a whole range of public information sessions, and we would do this during the week and on weekends because people aren't always available during the week, but really trying to make ourselves connect ourselves into that community and start to build awareness of the issues and the sort of systems they could build. We ran all sorts of demonstration days here. In the bottom left, we actually built a large rain garden on someone's property, and we invited people to come and look at what we were doing when we'd stopped moving machines around. We then solicited projects from the various private, the landholders from each household, and I'll talk about that in a minute. But we first needed to develop a method to assess the performance of the contribution of each project to our objectives. And so I've already talked about what were our hydrological and water quality objectives. And so we essentially developed a metric that measured for each project how much it would contribute to that runoff frequency, the volume, the quality of water, and etc. And so we developed that metric and applied it on a sort of standardized area of 100 square meters, etc. And we made that metric available to people using a web-based tool, so written in R, and here it's developed through the Shiny package for those of you who are such inclined. And so this is really Chris's great work. He probably won't want me to tell this story, but I tell you this story. But he often goes to his family-in-law for Christmas, and they live a long way in the outback, as we call it. And he sometimes gets a little bit bored with all the conversation, and so he locks himself in a little room somewhere in the house and works on things like this. And so one Christmas he basically developed a lot of this over Christmas, and so this allows a landholder to play around trying different things. I'm going to have a tank of this size, I'm going to have an infiltration system of this size, I'm going to connect my tank to these uses of water, etc. They can then see how much funding they could get from our project for that project. So it allows them to kind of do a little bit of gaming and come up with the optimal design of projects. We then use a market-based instrument to select projects. So we use what's called a reverse auction, where we essentially select the projects that deliver the best environmental benefit per dollar of project's cost. And so, for example, one person might, let's say 2 people are proposing a project that's going to cost $5,000 to build. And one of them decides, I really want this, so I'm only going to ask for $2,000 and I'll pay $3,000 myself. And the other person says, oh, I'm only prepared to put in 500, I'm going to ask 4,500. So let's assume for a minute that each gives the same environmental benefit. Then obviously the first project is going to be the one that's successful in the auction, or is more likely to be successful. And then of course projects will deliver different levels of environmental benefit. So this reverse auction allows us to rank the projects and select the projects that are best value, so that we're spending our limited money we've got for these works. We've spent about $3 million so far in the optimal way. So to date, this has resulted in around 300 retention systems constructed, ranging from very small scale at the private household to very large scale. So on the right hand side there, we've got a stormwater harvesting system with a storage capacity of close to 1 million litres, supplying a very large sports precinct and providing irrigation for those sports grounds. So if we think about, there are roughly 750 connected houses in the catchment. That gives you a sense of the level of coverage we're having over the catchment. So we have come close to disconnecting around half of those houses, or even more, using a range of these works. So if we look at this map, you'll see the blue and the 2 shades of green essentially represent our systems at all different scales, and you'll see that we really are having a pretty significant impact on the catchment. So all of those green and blue polygons represent little sub-catchments that we've dealt with, for want of a better term. Okay, so I'm sure you're interested, well, I hope you're interested to know, so what are we seeing? So I'll talk a little bit about what we might expect to see in a minute, but I'll just make the point that an important part of this project is monitoring at a range of scales. So we are not just monitoring at the stream scale, we're also monitoring at the sub-catchment scale, because we've got 3 tributaries. The streetscape scale, so we've got a paired catchment, as we call it, study where we're comparing one street where we've got all our systems with another street just outside the catchment where we don't have. And of course, we're doing a lot of measurement at the individual site scale. And so, for example, Perrine's PhD did lots of work on that. Okay, a really important part of this project is that we want to compare what we see to what we see in our control and reference streams. So we've got 3 controls, so similarly urban impacted but without our works, and 3 reference streams, so they're in a near natural state, because of course there are other things that are going to drive changes in the stream over time, climate, etc. And so our objective is really to see how much does our intervention stream move towards the reference stream and away from the control stream in terms of the ecological state and its water quality state. That's really the measure of what impact we've had. Our aim is to get it back to look more like a reference stream. So, to think about when we might start to see a response, it is very important to realize that if you look at the plots on the top right, that most of our works weren't completed until somewhere into sort of early 2013. So you'll see that the purple and the blue represent our systems there, and so the level of connected imperviousness is shown in red there, and you'll see that it really didn't start to drop significantly until about 2013. So we spent quite a few years building our systems. It really took a very long time it's a big job. And I'll just mention one quick thing here. You also notice there's a slight increase in you'll see a slight in the blue, just sort of below the green there, and that's because even while we were doing our systems, there were new impervious areas being created in the catchment as development happened and road upgrades occurred. And I'll talk a little bit about that because that was quite a problem for us and we had to find a way to deal with that. Okay, so I'm not going to talk much about the hydrology because we're in the midst of analysing that data, but just suffice to say that our site scale analysis show a lot of these systems are working quite well, quite variable, not all of them working well, but quite a few of them are. And we are starting to see some changes in the flashiness of the catchment, but it really is pretty early days. If we look at the ecological response, and I've highlighted in the right-hand side the yellow, just showing when the work's sort of finished. So it's really early days, and so far we don't see any significant response at all. So just to explain, the three blue lines are the reference catchments, the yellow lines are the control, so these are the urban bad sites without our intervention, and red is Little Stringybark Creek, and so from my plots that follow, it follows the same protocol. So if you're super optimistic or you're a politician, you might say that we'd seen a little increase in that last plot, but if you had any science training at all, you wouldn't claim anything. So far no ecological response. If we look, however, at water quality, this is total phosphorus with low S smoothing applied to it. So first of all, you'll notice there's a couple of big data gaps. So we can have a discussion later about the funding of long-term science, can't we? But you'll see what looks to be post late 2012, what looks to be a fairly clear drop in total phosphorus, moving from concentrations that were very similar to all the other urban catchments down much closer to the reference catchments. So early days, and our last sample was a bit more elevated again, and the low S picking that up and bouncing back up a little bit. So let's see over the next year, but here I'm more inclined to suggest we might be seeing something. Importantly, if we look at the relationship between flow and water quality, we believe we're starting to see an important response, that changes in flow and not having as big an impact on water quality. And what we think this means is that we are starting to get more subsurface flows, more filtered flows, and less sort of flashy mobilizing flows. So again, early days, but encouraging. All right, so I promised I would just highlight some of the lessons in terms of how do you run a big sort of experiment like this where you have to work with the community. Well, the first thing is that to deal with urban stormwater, you are obliged to work with landholders as well as big public land managers like councils, because a lot of the impervious runoff is coming from private houses. So if you exclude those, you're then going to make the downstream job much more difficult. The engagement of the community is not something you can just assume, and it's something you really have to work on. In our case, we were using a financial incentive, so a reverse auction, and there was a project, the Shepherd Creek project in the US, that used a similar method. So in Cincinnati, Ohio, so Alison Roy and Bill Schuster and others, and so what we found, some nice work done by Helen Brown and Darren Boss from our group, showed that there's a whole lot of things that are driving people to participate. The money is one, whether they have an environmental ethos, whether they trust the people who are involved, whether they trust the institutions who are involved. And then there's a whole lot of reasons why they might not participate. You make it too complex for them, you don't give them enough time, it's just not at the right time. There's a risk. So for example, in our first round, they had to pay for the works and then we'd pay them back, and a lot of people didn't bid to be involved because they didn't trust that, and I can understand that. And so we really, I think, learnt and showed that spending time working in the community over several years is really important. If you pick a catchment where you really want to do this, you're really also picking a community where you want to do it, and you work with that community. And for us, I think that's been a very important and also satisfying part of the project. We often get told, oh, your idea of working at the household scale is a bit silly because you're missing out on all the economies of scale, as in, it's always much cheaper to work at the larger scale. Well, actually, we really demonstrate that it's a myth that, it's something we all assume to be true, and yet our data shows that this is not necessarily true. Some of our most expensive systems were the largest ones, and in part because the large projects have big levels of risk and can go wrong quite dramatically. And so we found, particularly in our case, where we're building systems that are supplying water to the households, and that water has a value, so it's returning money to the household because they're saving water they'd otherwise have to pay for, that a lot of the smaller projects are actually less expensive. And if we look at our over time, we had 3 rounds of auction. Over time, we got smarter about the way we did it. Our smaller projects actually ended up being really quite a lot cheaper. One thing I mentioned is that whilst we were building all our systems, we found that there were new impervious areas being created at the same time, and so we worked with the state government and the local government to build an environmental significance overlay over the catchment, so a planning tool instrument that essentially requires anyone creating a new impervious area, even if it's council themselves, to use the same kind of measures we're using to deal with the stormwater problem. And this has really been a first in Australia for this kind of significance overlay to be applied, and so it's being seen as a pilot that'll be tested. All right, so where to from here? We're just about to finish the last round of work, so we'll do that in the next 6 to 12 months. We've just been given another $1 million to finish that off. And our big question is, can we measure a restoration trajectory? Just as we see a degradation trajectory with urbanisation, can we see a restoration trajectory? And we've now, with help from Melbourne Water, got another catchment that we're applying a similar concept to give a little bit more power to this. And we hope that if this works, we really demonstrate that applying these kind of principles is a way not only of restoring degraded catchments, but most importantly of protecting catchments that are going to be developed. Okay, I'll leave it there and I'll take any questions.
Okay, so if you have a question, you can go ahead and type it right into the chat box, and we will read it back to Tim. So we'll just give a moment for some questions to come in. And Tim, thank you so much for presenting today.
No problem. No, that's good. Okay, so I'll just read out the first question. So, a question from Aditi: what is the breakdown between ET-focused projects versus infiltration-focused projects? And do you expect more of an increase in ET or base flow? Yeah, so that's a great question. We used that Zhang curve. I'll just find out where that was. We used that Zhang curve to set that objective essentially. So we said that the percentage of the rainfall that should be infiltrated is, something like around 25%, and the rest of the water should be removed. So it's not primarily through ET, but through harvesting for use in the household. So these households are using the rainwater for toilet flushing, for hot water, for clothes washing, for irrigation of their lawns, for washing of their cars, etc. And that's probably the primary use of the water. But we also promote ET through some passive irrigation systems, etc. But our guiding principle is to try to get the water balance for that catchment back to somewhere near where it was in its pre-developed state, and we have the advantage of having the catchment right next door with the same climate and very similar physiography, giving us a really good reference. All right, I was asked to go to the slide on the environmental significance overlay, so I've just put that there. So Chuck, if you yes, you wanted to expand on the public acceptance. So yeah, this is a good question. So this overlay is fairly stringent. Anyone who's creating an impervious surface of 10 meters squared or more is required to use our systems. Adopt these kind of principles. One of the important things is that we got a really good partnership with Melbourne Water, who said, all right, to ensure that we are going to get good acceptance, why don't we use this as an opportunity to drive some innovation and maybe drive outcomes that are beyond just normal compliance. And so what we came up with is a similar, using our environmental benefit calculator, we came up with a scale of sort of performance, and people were, let's say there was sort of 10 units of performance, people were required to achieve a score of 6. Anyone who achieved greater than that could actually get some funding from Melbourne Water, and it was actually possible, if you really achieved a very high level of performance, sort of 9 and above, to get enough funding that it might actually cover the cost of the whole system. And so we didn't have a lot of, we really have had very little negative reaction, and we've had some, this is now applied to some sort of 50 new proposed developments in the catchment. So it's been really quite encouraging, and I think it's been quite important that we've got that carrot and stick together. All right, the next question was, do you think there's any upper limit on community participation in this sort of thing? In other words, could you ever get to 100% of homeowners to participate? Yeah, look, that's a really interesting question. When we started this project, we had very severe drought in Melbourne, and I know that California and Australia shared this problem a lot. And in some ways that made it easier, but that drought has sort of settled out. It'll come back, I reckon. But we're finding that we get about, our limit seems to be about 60% uptake. So if we go into a street and our coordinator goes around and talks to people, we can get about 60% uptake, and we don't seem to be able to do much better than that. I reckon if we really want to spend more money, we could, but at the limits we've set ourselves, we can't do much better than that. So perhaps there's some good discussions about how you might combine incentives with regulation. Okay, so a question about maintenance. So yeah, a really important question about maintenance. Do we expect the systems to be well maintained? And very importantly, are the systems on private allotments going to be better or worse maintained than those run by council? And it's easy to assume that a council would do a better job, but some of you might be laughing out loud now. We find it's certainly not guaranteed that council does a better job. We've started a project looking at this, and so we're doing some measurements to look at failure rates, but we reckon the failure rate at any particular time because a pump is not working or something could be something like 20%. And we are working with Melbourne Water and others to think about ways of dealing with that. And so one way could be that the water authority, rather than just supplying water through taps, they supply a service of water provision, which could include that they actually maintain your tank and that sort of thing at a cost. All right, so I'm just having a look whether you're able to install these treatments in series, or is the choice opportunistic based on who and what is being bid? All right, so the question is about hi Larry, by the way. The question is about whether how we assess bids, and that's a really important thing, that the environmental benefit calculator specifically not only assesses the benefit of that project on its particular site, but it takes account of what systems are already upstream, what systems are already downstream, etc. And so it's a full hydrologic model, meaning that, for example, if I've got two houses that are proposing to, they're exactly the same size house, exactly the same size systems they're proposing to build, so everything's identical, but on house A there's a infiltration system we've built downstream in a little local reserve area that's dealing with the kind of combined runoff, and on house B there isn't such a system, then house B would get higher priority in our system. So we are not just opportunistic. Of course, we're opportunistic in the sense that we can only respond to the bids we get, but the bids we're likely to fund are those that have the highest priority based on this model, and the bids we solicit are also affected by that, because after the first couple of rounds of auction we started identifying priority streets that we knew we couldn't do anything at larger scale for, and we had to deal with at the household scale. So we then go and really spend some effort trying to encourage them. All right. So Monica asked about we're not seeing the ecological benefit. So when I say ecological, no, I'm talking purely in the ecological metrics in terms of algal composition, leaf breakdown rates, macroinvertebrate composition, fish, which aren't a good metric in this catchment, but so I'm talking about those metrics. So we haven't seen those respond yet. I'm sorry, I know I flipped through that slide too quickly actually. I'll just go back to that. So this was actually, I should have explained, this was a diatom composition score. So we are starting to see changes in hydrology, but I say that with an asterisk because we've got work to do to work on that. But we are starting to see some changes in water quality, but in terms of the classic metrics of ecosystem response, macroinvertebrates, diatoms, algal composition, etc., we're not yet seeing a response, which is consistent with what we would hypothesize, that there is some lag between the physico-chemical changes and the ecological response. And of course there may be other things that limit it, such as geomorphic changes that have already taken place. So we'll wait and see for that.
All right, well, great. I think we are just about out of time. So again, Tim, thank you so much for presenting today. And this presentation will be archived on the Quasi website if anyone would like to take a look at it later. And we hope that you join us next week for Emma Rossi-Marshall's presentation.
All right, thank you very much, everyone. I've enjoyed it, and I'll look forward to being with you again next week to listen.
Excellent.
Okay, thanks a lot.
All right, thank you, Tim.
Bye.